have you ever really stopped to wonder how an AI actually learns? I mean, we hear all about these huge neural networks, but how do they go from, a total blank slate to something that can write a poem or spot a cat in a picture? Well, today, we're going to take a journey right into the heart of the AI brain.
It's the billion-dollar question, right? It honestly feels like magic sometimes, but it's not. The answer is actually hiding behind something that's surprisingly simple, but also incredibly powerful.
I want you to picture this giant, massive machine with millions, maybe even billions of tiny little knobs on it. And each one of these knobs can be turned just a tiny bit to the left or to the right. The combined setting of all of those knobs, well, that's what gives an AI its intelligence. And these little knobs, they have a name.
They're called weights, and this idea is the key to our whole explainer today. Weights are just numbers inside the AI that get tweaked and adjusted during training. They represent how strong the connection is between different artificial neurons, kind of like the synapses in our own brains. This is, and I mean this literally, where the AI's knowledge is actually stored. Okay, so let's dig into the basics. These weights are the absolute fundamental building blocks of AI learning, and in the lingo of machine learning, we call them parameters.
So a parameter is just any part of the model that's actually learned from the data it's given. That means every single one of those millions of weights, that's a parameter. They're these little adjustable numbers that the AI tunes over and over and over again until it starts getting things right. The final collection of all those values is the model's knowledge. That's the whole shebang. All right, so if a weight is just a number, how in the world does it learn anything? Well, it goes on this little journey, right? A constant cycle of trial and error. It makes a guess, it sees how wrong it was, and then it gets a tiny little nudge in the right direction.
And that little nudge, it comes from something called a gradient. The best way to think of a gradient is like a road sign for learning. So after the AI makes a mistake, the gradient tells each individual weight exactly what to do. Hey, you, increase your value just a little bit. Or you, dial it back a notch. It's pointing the way toward making a smaller mistake next time. Okay, so this right here, this is the fundamental loop of AI learning. Let's just walk through it real quick. First, the network takes a shot. It makes a guess. Step 2, it measures its error. Basically, it looks at how wrong its guess was compared to the right answer. Third, it calculates all those gradients we just talked about, those little road signs for every single weight. Then comes the magic part. Number 4, a process called backpropagation sends that error signal all the way back through the entire network. And finally, based on that signal, each weight gets updated, just a tiny bit. And then the whole cycle starts over, millions and millions of times. Backpropagation is so important, people call it the cornerstone of modern AI. It's just this really clever communication system. It's what allows the AI to figure out of its millions of weights, exactly how much each one contributed to that one mistake at the very end. It's like a chain of command for accountability, It makes sure every single part of the network learns from the final outcome. It's brilliant.
Now, as you can imagine, just letting millions of weights all change at once can get pretty chaotic. The system can start learning the wrong things, or just become totally unstable. So AI developers came up with a set of rules. You can think of them like guardians that keep the whole learning process on the right track.
A really common problem is when the AI gets too good at the data it's training on. It's not really learning, it's just memorizing the answers. This is called overfitting. And what it means is that the AI will seem like a genius on the stuff it's already seen, but it'll be absolutely terrible at predicting anything new.
So the main guardian against this problem is something called regularization. It's basically a bunch of techniques that add a penalty for being too complex. It's like telling the AI, hey, I want you to find a solution, but I want you to find the simplest, most elegant solution possible. It encourages the weights to stay small, forcing it to generalize instead of just memorizing. And there are two main flavors of this guardian. You've got L1 regularization, which is kind of like a minimalist. It's so strict that it forces some weights to become exactly zero, pretty much kicking them out of the network. Then you have L2 regularization, which is more of a team player. It just penalizes any single weight that tries to get too big, encouraging all the weights to contribute just a little bit.
Another super important guardian is called clipping. Just think of it like a safety rail. See, sometimes during training, a weight's update signal can be so huge that its value just explodes to some ridiculous number, and that can throw the entire network into chaos. Clipping is simple. It just sets a hard limit, a ceiling and a floor, saying, nope, you can't go higher or lower than this. It keeps everything nice and stable.
Okay, so once an AI is trained, what you have is this massive network of finely tuned weights. The next big challenge is making them all work together as a team, as efficiently as possible.
You see, a fully trained model can be absolutely enormous and really slow. We're talking billions of parameters sometimes. So the goal isn't just to be accurate, it's also to be efficient. And this has led to some really clever strategies for getting all these weights to collaborate better. So here are 4 key strategies. Pruning is kind of like trimming a bonsai tree. You just snip away the weights that aren't really doing much. Sharing is a really cool trick where you reuse the exact same set of weights in different parts of the model to save a ton of space. Freezing is what you do when you're adapting an AI. You basically lock in the old knowledge while you train a new part of the network. And then there's exchange. This is also known as transfer learning, and it's where you literally take a chunk of learned weights from one AI and transplant them into a new one to give it a massive head start.
So after all this training and adjusting and optimizing, what's the end goal? Where are we actually trying to get all of these millions of weights to land? Well, the answer is a place that researchers like to call the zone.
The idea is to find what researchers call a region of equilibrium, a basin of convergence. So what does that actually mean? Well, the key thing to understand is that the zone isn't one single perfect number for each weight. No, it's more like a stable neighborhood, a sweet spot where the model just performs really well, finding that perfect balance between being accurate and efficient.
And this is what it's all about. When all the weights find their zone, the AI stops just memorizing things and it starts to truly generalize. It can take what it's learned and actually apply it correctly to brand new situations, to data it has never, ever seen before. And that is the real sign of intelligence. So, from a single, tunable little knob to a network of billions all working together in perfect harmony, the journey of a single weight is really the story of how AI learns. And it kind of leaves us with this one big, fascinating thought. If we can really guide every single one of these connections into its perfect zone, what are the real limits here? What problems are left that an AI won't be able to solve?